Okay. So the last thing we did, we said that we have our setup, right? Okay. And we are going to use a meter ruler to measure the length or the unextended length of the spring, right?
Yes.
Okay. 9. Slowly pull the string upward, watching where the magnet becomes detached from the card. Take 2 readings for the extended spring S1 dash and S2 dash. Calculate the average extension S dash equal S1 dash plus S2 dash. Divide 2, right? So what we are going to do, we are going to pull the spring, watching when it becomes detached from the card. Okay? And we are going to measure
Okay.
this extension. We are going to do it twice, as usual. Then we are going to calculate the average extension. Now, or extended length to be more accurate. How we are going to calculate the extension, Dim?
Um, S dash minus S naught.
Exactly. Calculate the extension S as S dash minus S0. Okay, right? Now, what is the next step?
We will find the other. We will find the independent variable.
We are going to repeat our
The
measurement, right? Using different card widths, right? We are going to vary the independent variable, meaning we are going to vary or change t and repeat the whole thing again, right?
Yes.
Repeat your measurement for different cards with different thicknesses t. Tabulate your measured values in the table below. Okay, right? Are we good?
What does tabulate mean?
Put the results in a table.
Okay.
Okay, we are going to make a table. Tabulate means the finding you get, put them in a table format. Okay?
Okay.
Okay. Now use a vernier caliper What do you think we are going to use the vernier caliper for?
Measure the diameter.
No, we have already done that. To measure the thickness T of the card. Take at least 2 readings and use the average. Okay. Now, it is time to go back and take a look at the equation. It is now time to go back and look at the equation. So what do we have for the equation, Dean? We have Ks is equal A L B Z over T. Right? This is our equation, right?
Right.
Now try to rewrite it into a form which looks like that of a straight line. Can you think of a way to do that? Now, remember, let me show you it here. So, what do we have? K S is equal A L B Z divide T, right?
Yes.
What do we know about the equation of a straight line? Y is equal
Mx plus
X
C.
plus C, right?
Yes.
Okay. What do we have over here? Dependent. What do we have here?
Independent.
Independent. What about this? Gradient.
Gradient.
What about this?
Y-intercept.
Intercept. Okay. Can we divide this equation to have dependent on one side and independent on the other side?
Yes.
So what is the dependent over here?
Is the extension. Z.
S? No, S, right?
S. Yes.
S. And what is the independent?
The thickness.
Thickness T.
T.
Or something related to T. We better say it like this, something related to T. So maybe I should write it like this. S is equal A L B Z divide K. Can you
KC.
see? Here are all constants. Are all constants. Okay? Are we
Okay.
good? 1
Yes.
over T. 1 over T. Is that okay?
Yes.
Okay. Does it look like one of a straight line that we know of?
No.
Why?
Yeah, yes, it does, because they are to the power of 1.
Sorry?
They are to the power of 1.
This is to the power of 1. What about this one? Actually, this one is to the power of what, Dean?
-1.
Minus 1. What about the intercept?
1.
No. Intercept is 0, right?
Yes.
Okay, the intercept is 0. It is just 0. There is nothing like anything over here, right? So the intercept is 0. So this is an equation of a straight line that passes through the origin. So the straight equation y is equal mx of a straight line that goes through the origin. The intercept is 0, right? Now, what do you think we should make a plot between S and T or something else?
S and T.
Okay, but remember, T is to the power minus 1.
Yes.
Okay, so if we make this plot, we are not going to get a straight line. We're going to get something like this. So what do you think else we can do to get a straight line? So if I tell you, write this part, if you can just imagine, I have brackets here and I make it to the power of 1. Can you tell me now what should I make a plot of?
S and T negative 1 with bracket.
Actually, it's not, but I can say that I'm going to make S and T to the power minus 1. Right?
Yes.
Okay, which is S 1 over T. Can you see now how we are going to proceed? This is very important, how we can handle this type of equations, Dean. How we can change an equation into that of a straight line. Okay, so this equation did look
Okay.
like this. It is obvious that T is not rise to the power 1. So we cannot do that. What if T was something like this? How we can change this equation to that of a straight line?
We will make a bracket and write to the power 1.
No, it is not we are going to do a bracket, but we are just going to look at this independent variable. The whole of this independent variable, it is 1 over T square. Okay? Then what we are going to make a plot of S and 1 over T square. Okay? Can you
Okay.
see how we are doing it?
And the equation will be straight line, right?
Yes. If we make a plot of S and 1 over T square as he's telling us, then we are going to get a straight line. What if the equation did look like this? Log T. What should we plot to get a straight line?
Log T.
S on the y-axis and log T on the y-axis, okay? Is that
Yes.
okay? Okay. Now for
Yes.
this experiment, is telling us it is 1 over T. So we make a plot of S on the y-axis and 1 over T on the x-axis. Now let us go back. So we rewrite this equation as S is equal A L B Z divide K 1 over T. Now we make a table that can hold all this information. So first, what do we have?
S.
S and the units. No, sorry, it is not S, it's T. We first, always the first column is the independent variable. T in what? The units.
Meter.
Sorry?
Meter.
Meter or centimeter, okay? Let us say it is in centimeters. What about the other thing, S? It is also going to be in centimeters, right?
Yes.
What else do we need in this table?
We need ALBZ over K.
No, this we don't need. If we compare it to the equation of a straight line, what are these?
The
This whole
gradient.
bunch of things.
Gradient.
Gradient, the whole thing is the gradient. So we don't actually need them in the table. The table only holds things that they are going to vary, that we vary, and those that we measure, or then what we calculate, and things that we need to make the plot. So what else here in the table that we need to make the plot?
Nothing.
No, why? How come? What is the plot going to be look like, Dean? What is in the y-axis?
S.
S. What is in the x-axis?
1 over T.
1 over t, right? So to make the plot, we need S and 1 over t. What do we have here?
T and S.
T and S. Can we make a plot of using only these values?
No.
We need what else?
1 over T.
1 over t. It's going to be the units
Centimeter inverse.
minus 1, right? So,
Yes.
okay. Now, make a graph plot of S y-axis and 1 over t x-axis and calculate the gradient. Okay? Now we tell him gradient is equal to what?
ALBZ over K.
LB Z over K, right?
Yes.
Now he is asking us the final thing. Calculate, or how should we determine Z, right? He's asking for Z.
Yes.
Therefore, Z is equal K, right? Gradient divide A L B, right?
Okay.
Okay. Can you see it?
Yes.
Okay, good. Now we are almost done. Now we come to the last part. It's telling us any safety precaution to be taken.
We can say wear a lab coat.
Maybe, yes, but usually we get things relevant to this one. Things like caution should be taken when handling the spring and magnet. Okay, something like this. Another thing that I think we have passed the allowed area. Okay, because we are doing some explanation over here, but okay. Another thing, you have to be careful with the area. I missed it this time. Make sure to carry out the experiment away from any other magnetic materials. Okay? For example,
Okay.
okay. But never write like I did now, Deem. Okay?
Okay.
Okay? I think I have missed it. So never write it like this. Are we okay? So now let us go through how, because this is how we are going always to answer this question. Okay? You look at all the parameters that you have in the equation. You define them in a similar table. This is going, if you write them in this table format, it's going to help you answer them properly, right? Okay?
Okay.
Okay. Then we are going to decide which parameters are going to be the control parameters, and we are going to keep them constant. Like the length, the cross-sectional area, the magnetic flux, the spring constant. Okay? These we need to measure, but we are going to keep them constant throughout our investigation.
Yes.
Now, we need to decide which is the dependent and which is the independent. How to know them? Most probably are going to get something like this statement. It is suggested that S is related to T. For example, are going to get something like this statement. So from here we can decide which one is the dependent and which one is the independent. How we decide that? The dependent is the one that we are going to measure. Okay? The independent is the one that we can easily change ourselves, we control. For example, the width of this card, it is something that we can control. I can use a card with 5 millimeter, 10 millimeter, 15 millimeter. This is something I control. So this is going to be the independent variable, right? Then how you proceed? You tell him exactly how you are going to measure each single control value or control parameter. I'm telling him how I measure the length, how I measure this, and how I measure that. Okay? Are you following them?
Yes, I am.
Okay. Then we are going to tell him for the control variables that are kept constant, we are measuring them twice. And we are calculating the average or using the average for further for the rest of the experiment. Okay? Then we are going to tell him that we vary the independent variable and we measure the corresponding dependent variable. We just need to formulate it in a language relevant to the experiment. Okay? But this is what we actually do. Vary the independent and measure what? The independent. But we are going to always formulate it or write it in a language relevant to the experiment we are at. Then we are telling him from the equation what is going to be the gradient. And we are going to decide what we are going to have in our table. Okay? Like T, S, and 1 over T. The table should always have all the information that you vary, that you measure, and then what you calculate to make your graph plot. Okay? Are we good?
Yes, we are.
Okay. Then you tell him what is the gradient, make a graph plot of so and so, which is going to be what in the y-axis and what is on the x-axis. Okay? What is the gradient going to be? And how we can calculate the constant that he asked for. For this equation, it is only the gradient. Sometimes we need also to calculate the intercept. It will depend. Okay?
Okay.
Okay? Then we can write something about quotients that we take. It will also depend on the experiment. So there's nothing like a clear what should we write here. Okay? Are we okay, Adim?
Yes.
Okay. So let us proceed to question number 2. He's now telling us a student investigates the resonant frequency of a metal rod. The metal rod of length L is suspended from 2 rubber loops. A sensitive microphone with a cone is positioned at one end of the rod. The microphone is attached to an oscilloscope. Okay, and he's showing us the setup. The rod is hit gently with a hammer. The period T of the trace produced on the oscilloscope is determined. The experiment is repeated for different values of L. It is suggested that T and L are related by the equation. So he's telling us what is the dependent and what is the independent. Okay? So from this statement, Dean, can you tell me what is the dependent and what is the independent?
L is the
So what is L?
L is the independent.
L is the independent. Why? Because he's telling us we are changing what? It is repeated for different values of L. So it is going to be the independent. What is the dependent?
T.
T. Okay, this is good. Now he is telling us where C and N are constant. C are N constant. So most probably those are the values we are going to calculate from the gradient and the intercept. Now he is telling us a graph is plotted of log T on the y-axis against log L on the x-axis. A graph is plotted of log T on the y-axis against log L on the x-axis. So, what do you think we should do to this equation?
Multiplied by length.
No, we don't say multiply. We say apply the log. It's telling LG, it is log. Okay? What we say, it is not multiply. It is apply the log to both sides. Okay. So how we are going to apply the log?
I'll say log T equal
T is equal
N to log L.
sorry? No, let us do it in steps.
N.
Let us do it in steps. This log, this whole thing. Okay?
Okay.
Okay. Remember, log AB is equal what, Dean?
Log A plus log B.
Plus log B. Good. So, let us say that this function, this is part, and this is another part multiplied together. Then I can say it is log 2 over C, right? Plus log ln, right?
Yes.
Is it okay?
Yes.
Okay. Do you remember log x to the power n, how we can write it?
We'll say N log X.
N log x, right? So here, is that okay?
Yes.
Can we write it as an equation of a straight line? Remember, y is equal mx plus c. So in this equation, what should go for the dependent?
The dependent is the T.
It's not t,
Log T.
log t. Be careful. What is going to go for the independent?
Log 2 over C.
No.
N log L.
N log L. The independent is log L, right?
Yes.
So what is the gradient?
N.
N. What is the intercept?
Log 2 over C.
Yes. So the gradient is N. The intercept is log 2 over C. Okay?
Okay.
Can you see how we are going to do that? Make sure to get yourself comfortable with the log function and how we apply it. Okay? Because most of the time, most of the equation we get, it involves using either the log function or the ln function. Okay?
Okay.
So now he's telling us values of L and T are given in this table. Okay, we have L and T. Calculate and record values of log and log T in the table. Include the absolute uncertainty in log t. Include the absolute uncertainties in log t. Okay? Can you see in this table? We have L, right? We have
Yes.
T, but we also have the absolute uncertainty in this measurement. Okay? Now, what we would like to do is log L first. Let us go with log L first. Let us get our calculator. For the first one, it is log 54, right? Can you see it, Dean?
Yes.
Okay. What do we get? 1.732, so and so. Is it okay?
Yes, two significant figure.
Why we are keeping
Or three.
not two decimal places? For the log, we look at the decimal places. We are going to keep two decimal places. Why we are keeping only two decimal?
Because in the L, it is two significant figure.
Yes. So two significant figures translates in the log function or the lim function to two decimal places. Okay?
Okay.
Okay. So it is going to be 1.73. Now, let us do another one. Log 70. 1.845. What should we record?
1.85.
Exactly. Okay, let me do the last one. Log 167. What do we get? 2.22227.
2.22.
No. How many significant figures do we have here?
3.
3. So how many decimal places should we keep?
3.
3. So it is going to be 2.223. Okay. Can you see it? 2.2. Here, 3 significant figures. I'm going to 3 significant figures. I'm keeping here 3 decimal places. This is for the log and the len function. Okay?
Okay.
Can you do the remaining for yourself?
Yes.
Okay. I think our time is running again, so we come back in 10 minutes. Can you do the
Okay.
remaining for me and then tell me what did you get?
Okay, but I don't have the paper.
You don't have the paper. Okay. 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 Can you make a quick screenshot?
Okay.
Okay. Make a quick screenshot.
I did.
Okay. Then you just tell me what did you get. Okay. Then see you in 10 minutes.
Okay.
Okay. Can you help me complete the table?
Okay.
For the log L.
After 1.85, it is 1.93.
Okay. Good.
Then 2.03.
0.3 only?
Yes.
No, we have 3 significant figures. So we
Okay,
need
let me do
2
it again.
decimal places. Okay?
2.033.
Yes. Okay. What is the other one?
2.146.
Exactly. completed with column number 2, right? Or the column for the log of L, right? Now let us do column for the log T. Okay? So what are going to do?
We will just write log 24 in the calculator, right?
Yes. But remember, what did he ask us to do else? What else did he ask to do?
Include the absolute uncertainty.
Yes, in T, in log T. So log 24.
Log 24 is 1.38.
Log of 24 is 1.38, and we keep 2 decimal places, right?
Yes.
Okay. Now, how we are going to calculate the absolute uncertainty in the log? Do you remember? I gave you an equation for that from last time. Do you remember?
No, I don't.
Okay. So delta log, okay, is equal the log of the maximum minus log of the average. Log max minus log average. Okay? Now, what is the max? The maximum, right? How we can get the maximum?
Yes.
Okay?
By solving.
Sorry?
By completing the table.
Yes, but how can we get the maximum? Look at this value, Dean. It is 24, right?
Yes.
And plus or minus 1. What does
Yes.
that mean?
Mean they are not sure if it's 25 or 23.
It is 25 as the maximum. And
23 as a
the
minimum.
minimum. But it is somewhere. Right?
Yes.
Okay.
Yes.
So this is the maximum. And this is the average. Okay? So it's going to be log 25
minus log 24.
log 25 minus log 24. Can we do it on the calculator?
Okay.
Log 25 minus log 24.
0.0177.
Yes. And always in the absolute uncertainty, keep 1 decimal place. One significant figure. We only keep 1 significant figure. Okay? So how we are going to write this number to 1 significant figure? Nadine?
مستر صوتك قطع ما سمعته.
Okay, how we can write this number to 1 significant figure? So we always keep the absolute uncertainty to 1 significant figure, okay?
Okay.
Okay, so how can we write this number to 1 significant figure?
0.02.
Yes, 0.02. Okay, this is good. So it's going to be plus or minus 0.02, right? Let us do another one. Can you do it ahead of me?
Yes, it is. I did it. I did all of them.
Okay, let me check. Log 32.
It is 1.51.
1.51. Can you do the absolute uncertainty?
Okay, it is log
Yes.
minus 33
Yes.
minus log
Okay.
32,
Yes.
which
And
is
keep.
0.01.
Okay, good. Can you do another one?
Yes, it is 1.59
Okay. Absolute.
and 40 log 40 minus
Yes.
log log 39,
Yes.
which is 0.01 also.
Okay, good. So let me continue. Do the rest, 1.69, and check with me. Are you getting the same results?
Yes, I am.
Okay, good. So now we have completed our table. We have completed our table. And this is our graph. And he's telling us log L on the x-axis, log T on the y-axis, and they are kind enough to give us the scale already on the x and y-axis. Okay?
Okay.
Okay, this is good. Now let me try to make the plot. Okay. Let me copy.
Did they tell us which one in the Y and which one in the X?
Yes, it is already there, right? Log.
Oh, okay, yeah.
Okay, and log. And he's also telling us over here. Okay, so just a reminder to remind us. We just write over here x axis, y axis. Okay?
Okay.
Okay. Now just let me, just to help us, we are making the plot. Okay? So we have these values for log on the x-axis and the y-axis. Notice here dim. Now, this is new. Draw a straight line of the best fit and the worst acceptable straight line on your graph. Okay, sorry. Let us read this one first. Plot a graph of log T against log L. Include error bars for log T. Okay? So, something new is this thing of error bars. Right?
Yes.
Making a graph plot with error bars is a little bit new, right?
Right.
So, let us take our time and see how we're going to do that. Now, let us see. We have on the x-axis 1.73. Right?
Right.
Okay, good. Now, so the first thing to do, as usual, is to see what is the x-axis. So 1 square is equal 0.1, right?
Right.
Okay. Now, how we can represent 1.73?
I will say 1.73 minus 1.7 divided 0.1.
Okay, 1.73. If you would like to do it like this, minus 1.7 divide 0.1. It is going to get 0.03 divide 0.1 is equal to 0.3. Okay, did you get 0.3?
Right, yeah.
Okay, what does 0.3 means?
Go 3 small cubes.
3 small cubes. So 1, 2, 3.
Yes.
Okay, it is our here, right?
Right.
Okay, now for the y. 1.38. Again, 0.1, right?
1.38.
Yes.
Yes, 0.5. 0.05.
0.05. Okay, 0.05, sorry. Okay, then what we are going to do?
What is the number that we want?
1.38.
Okay, so I'll say 1.38 minus,
Right?
can you go down a little bit? Okay, minus 1.35
Okay.
equals 0.6.
0.6. Let me check it. I think it is okay. 1.38 minus 1.35 divide 0.05. 0.6, right? Meaning what?
Yes.
Meaning what?
We'll go 6 small
6
cubes.
small squares.
We'll go
So
6
1,
small cubes.
2, 3,
Yeah.
4, 5, 6. Right? This one.
Yes.
Okay, good. Now, what about the error bars? This is
Right.
the new one. This is new. And we know the error bars are going to be in the y-axis. The error bars are going to be in the y-axis. So, to draw the error bars, look at this value. Look at this value. 0.02. Okay, Dim?
Okay.
Divide by the scale.
0.05.
Yes. How much do we get?
0.4.
0.02 divide 0.05. We get 0.4, meaning what? 4 small squares. Right?
Yes.
Okay. So this is how you do it. Starting from your mark. Let me zoom in a little bit so you can see it. So starting from the mark, count 4 small squares upward. Meaning what? This is 1, 2, 3, 4. And make a line like this. Sorry. 1, 2, 3, and 4. Here is 4. Okay?
Mister, where is the mark?
Sorry? This is the mark.
The X?
Yes. It is the point where we mark
Okay.
for the data point, right?
Yeah, okay.
Okay. And since it is in the y-axis, we are going to count 4 small squares upward. Now, what else should we do? We count 4 small squares downward. 1, 2, 3, and 4. Can you see what I'm doing?
Yes.
Okay. So it looks like this. Are we done? No, not yet. We are going to make a straight line like this, Dean. Can you see how it looks?
Yes.
Okay. So meaning what? So let us see what does it mean. We have this data point, right?
Yes.
But we are really not uncertain about it. It could be as high as here or low at this. Can you see what does it mean when we do this error bars?
Yes.
Okay. It is the value,
Okay.
it is the point here. But it could be as high as 1.4 or as low as 1.36. Okay?
Okay.
Is it fine with you?
Yes, it is.
Remember, we did the one on the on the y-axis because the error bars we are given on the y-axis. Okay?
Okay.
Sometimes we get it on the x, so we have to be cautious.
Okay.
Okay, good. Let us
Okay.
do another point. Now, can you help me with that? The other point,
Sure. Yes,
it is
but
1.85.
I can't see it. Yes, now I can.
1.85 and 1.51. Right? So let us
Yes.
do the points first. So 1.85. How we are going to do that?
I'll say 1.85 minus 1.8
Yes.
divide 0.1.
Well, okay, yes, this is good. But there is, for this example, it is easy to calculate, right? Because remember,
Yeah,
what is a
yeah.
small square?
0.1.
No, small one. What
It
is it?
is 0.01.
0.01. So this is 1.81, 1.82, 1.83, 1.85, 1.85.
Right.
Okay, so sometimes it is easy, right?
Yeah.
It will help us save time. But if you are comfortable doing it this way, that way, okay.
Okay.
Okay, good. So it is 1.85 and 1.51. 1.51. It should be a little bit up here. Okay. So, can you do it yourself?
Yes, I will go to a cube
Exactly.
from 0.5.
Yes, from 1.5. So do you agree it is over here?
Yes.
Okay, good. Now we go to the error bars. We got 0.01.
0.01 divided 0.05. It
Okay.
will give us 0.2.
0.2. So how we are going to do?
I will go 2 block above the mark and 2 block below the mark.
Exactly. Like this. What else should I do?
I'll draw a straight line.
I draw a straight line connecting them. Right?
Yes.
Going through the point that I already marked.
Yes.
Are we good so far?
Yes.
It is just a little bit time consuming, but okay. So the other point, 1.93 and 1.59. 1.9. 3 and 1.59. Let us see. 1.93. Now, this is 90, right? 93.
I'll go 3 blocks from 1.9.
Yes. 1.9. Yes. 1, 2, 3. Here. 1.93. Okay. And what about 59?
I'll go 8 blocks from 1.55.
Exactly. Good. Exactly. What about the error bar?
It is 0.1.
Yeah, 0.01.
So I'll go two blocks above the mark and 2 blocks below the mark.
Okay, 1, 2, and 1, 2, right?
Yes.
I'm good.
Then draw a line passing through the mark.
Okay, good. Now 2.03 and 1.69. So this is 2, right?
Yes.
And this is 2.1. Sorry, 2.01.
Yes.
It's 2.01. It's 2.02, 2.03. So it's 3 marks from 2. And
Yes.
1.69. Again, 3 marks over
It is
here.
8 blocks.
Exactly, 8 blocks. And the error bar is 0.02, right?
Yes.
Okay. Then how many squares?
4 squares above and 4 squares below.
1, 2, 3, 4. 1, 2, 3, 4. And we draw the line. Are we good?
Yes.
2.146. And 1.81. 2.46. And 1.81. 146, sorry. So what do you think how we can go do that? This is 2.1, right?
Yes.
Okay, 2.1. This is 2.11, right?
Yes.
2.12, 13, 14. And this is 2.15, right?
Yes.
So it is in between.
Right.
Okay? So it is around here. Now, what about 1.81? How many squares up?
2.
2. So it is here. The error bar is 0.01.
It is also 2 above and 2 below.
2 above and 2 below. That was easy. So it is 2 over here and 2 over here. And we do the straight line. Okay? Now,
Okay.
2.223 and 1.87. 2.223 and 1.87. 2.2. Okay, so this is 2.2, 2.21, 2.22. Here is 2.23. right?
Yes.
So it is between this one and that one. Closer to 2.2, right?
Right.
If you don't like to do it this way and you feel a little bit confused, you can do always 2.223 minus 2.2, right?
Right.
Okay. Can we do it quickly in the calculator? Two point two two three minus
0.23.
yes, divide 0.1, 0.23. So it is two small squares and a little bit further away from it, right?
Right.
Okay, good. So, and what about the 1.87?
4 blocks from 1.85.
Yes, exactly, good. Now you know how to do it.
Yes.
Okay. 1, 2, 3, 4. Over here, right? And the error bar is 0.02. So it is 4 up, 4 down.
Yes.
Are we okay?
Yes.
Okay, good. Now we are done with this part. Sorry. You have any question in this part?
No, I don't.
Okay, then I think you got the idea. Now, Dim.
Yes.
Okay. Now, you remember when we used to draw a straight line? What did we typically do?
We draw a straight line.
When we used to do a straight line for how it passes through the points. We would typically go for the line that goes through almost the center of
Most
all the
point.
lines, right?
Yes.
Like this. Can you see?
Yes.
This line I am trying to get. Okay.
Okay.
So this line, I think, can go almost through most of the centers of the lines or the points. Can you see it?
Yes, I can.
Okay. It can go up to almost all the centers. So this line that we can use, draw it to go through most of the centers of the data points, we call it the line of best fit. What should we call it? Line
Line of best fit.
best fit. Okay? Line of best fit. Now, two more lines can be actually drawn in this figure or this graph. Which line do you think? Let me change the color. Okay. And the style. So Can you see the figure? Two more lines I can draw. One, I can call it the line with the maximum gradient. The line with the maximum gradient.
Gradient.
Let us see how this line looks like. It is the green one. Can you see this green one?
Yes.
Okay. Look how it goes. It doesn't go to the center of the lines, the data points. I try to make it go through as close as possible to
The uncertainty.
Yes, the bottom of the uncertainty here and the top of the uncertainty over here. Okay?
Okay.
Can you see it? So if I
Yes, I
compare
can.
the gradient of the green line and the red line, I can see that this green one got a larger gradient than the red one.
Okay.
Okay, so the green line, green line with maximum gradient. Okay? Now another line can be drawn. What do you think this line would look like? What do you think, Deem?
The smallest gradient.
Smallest gradient, right. So how I'm going to do it?
From the top of the uncertainty to the lower.
Usually, yes, it is right, but sometimes I just need to see how I can do it, right? This can be look like this.
Yes.
Okay, can you see it? How it looks? It is
Yes.
missing this point. So this doesn't look good. It is totally missing this point. So this line is not okay. Okay? I'll try to fix it.
Yes.
So I try to make it like this. Okay. Almost. Okay.
Okay.
So this is another one is the line with the steep, shallowest or minimum gradient. The line with the minimum purple
Gradient.
line with shallowest gradient. So in any exam, you will be asked to draw two of them. One of the best fit, and you can then choose the worst. It can be the maximum or the minimum. The one you choose. You don't have to draw three of them, right? Then one of them is going to be the best, and the other one is either going to be the maximum or the minimum. It is your choice.
Okay.
Okay?
Okay.
It is totally your choice.
Mister,
Yes.
I have a question.
Yes.
So to be minimum, it should be above the straight line,
It's going to be low.
lower than the straight line.
Yes. Yes. You see, let me show you this very quickly. if I have this straight line, okay? I have this straight line. Can you see if I draw another line like this? Another line like this. So this one, it looks steep, right?
Yes.
It is closer to the y-axis than this one, right?
Right.
So this is maximum gradient. If I draw another line like this, so it is further away from the y-axis than this one. Then this is shallow line or less gradient. Okay?
Okay.
But it is going to be your choice. The one that goes through most of the data points, the center of the data points, is going to be our best fit line. Any other one that goes through most of the data points, okay, like this, it is either going to be the maximum gradient or minimum gradient. It is your choice.
Okay.
Okay? Okay, good. Determine the line of best fit includes the absolute uncertainty in your answer. So this is how we are going to do it. We are going to calculate the gradient for the two lines. Do I need to show you how to calculate the gradient?
No.
Okay, you draw two right angle triangles, right? For each line, independent of each other, okay?
Okay.
Okay, and you calculate the gradient for both of them. So I'm going to do, I say best fit. I got the gradient is 1.85 minus 1.47 divide 2.2 minus 1.85. I get 0.987. I calculate the one of my choice. I just call it worst fit. Okay? I call it worst fit. I think, Dim, we come back in 10 minutes.
Okay.
Okay? Can you see?
Yes.
Okay. So this is where we stop. So we calculate the gradient for the best fit line. Okay. And we also calculate the gradient for the worst fit line. It could be the shallowest or the steepest. It doesn't make a difference. Okay. Is that okay with you, Deem?
Yes, it is.
Okay. So we are asked to determine the gradient of the line of best fit includes the absolute uncertainty in your answer. This is how we do that. We calculated the line of best fit. To calculate the uncertainty, we know how to do that, right?
Yes.
How we do that?
Maximum minus average.
Maximum minus the average. And what is the average?
It is 0.9 87 plus 1.026 divided by 2, which gives us
No. Use directly this one as the average.
which one?
The one of the best fit.
Okay.
Okay, we use directly the average because we call it the best fit. And you can see it is between both two lines, right?
Yes.
Okay, so we consider this one to be the average.
Okay.
So the uncertainty in the gradient is going to be the average minus, it is going to be the maximum or the minimum. We don't make a difference. It is going to be a negative sign, right?
Yes.
Small minus big. Just ignore the sign.
Okay, it is 0.039.
0.039. Okay, we keep it to how many significant figures?
To 3.
No, the absolute uncertainty.
To 1 significant figure.
One significant. So how are we going to report this?
Plus or minus?
Yes. 0.04, right?
Why 0.04?
Because it is going to be to one significant figure, right?
Yes, I meant, oh, okay, yes, I got it.
This is the absolute. But what is the value for the best fit? Point
0.87.
No. Look at here. Since we are reporting the absolute uncertainty to two decimal places, also keep the average value to 2 decimal places. Okay?
Okay.
Okay? So the absolute, one significant figure. The average, to the same number of decimal places. Okay? So it's going to be 0.99. Okay?
Okay.
Do we have units? Did we miss the units for the gradient?
Yes.
Can you check? So do we have units over here?
Yes, we have
What is the units?
second per centimeter.
Huh? No, don't be
Second.
fooled. The log doesn't have units. The log of the function and the ln of the function doesn't have units. Okay, Deem?
Okay.
The centimeter is for the value inside the log function. It doesn't have units. We have units over here. We are good. Okay? Okay?
Okay.
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 Determine the y-intercept of the line of the best fit. Include absolute uncertainty in your answer. So, can we read the intercept from the graph?
No, we can't.
We can't. Why?
Because the x-axis doesn't start from 0.
Because the x-axis doesn't start. So we need to do some calculation. What are we going to do? Write
Y
the
equal
equation.
mx
Y mx plus
plus c.
c. C is equal y minus
Y minus mx.
mx, right?
Yes.
Okay. Now we have the best fit value for the gradient, right? It is
Yes.
0.99 or 0.987. It doesn't make a difference. 0.99 or 0.87. We are going to use this one. Okay. So, and what else do we need to calculate? The intercept.
We need to find 2 points in the
Sorry?
line. I need to find 2 points in a line.
One for the best
1
fit and
point.
one for the worst fit, right?
Yes.
Okay. So I picked those two lines. I picked this one for the best fit. 2.2, 1.85. This is a point on the best fit line. For the worst fit line, I take this point. Okay? Those are two different points. Now, let us do the calculation. So, for the best fit, it is going to be y2 1.85, right? Minus, what is the gradient?
1.99.
0.99. It's not 1.99. Remember? 0.99. Okay? So y 1.85 minus 0.99 times what is x? What is x, Dean?
X is 2.2.
2.2, yes. So we do it in the calculator, we get minus
Negative
0.328.
2.8.
Okay? We repeat
Okay.
that for the best, this is the best fit. We repeat it for the worst fit. So it is 1.85 minus, now we use the gradient, this one, 1.026, right? Are you following with me?
Yes.
We calculate. Okay? Are we good?
Yes.
Okay. Now, which one should we use?
The average.
The average? No. Always the one with the best fit is going to be the average. Okay?
Okay. Yes.
Can we calculate the uncertainty?
It is 0.4.
0.4? No. How did you get that?
From the worst fit.
Yes. But how we calculate the uncertainty?
So 0.4 divided 0.05.
Why is that? It is going to be this one minus the best fit or minus the average. The worst minus the average. The maximum minus the average, right?
Okay.
This is always how we calculate the uncertainty, right? We have two
Yes.
values. Average. One is worst. Could be the maximum or the minimum. Doesn't make a difference. So it is the difference between them. And we don't care for the sign.
Okay.
Okay? So what do we get over here?
0.0.
How much?
0.08.
0.08. And you kept it to one decimal place. One significant figure, right? So how we are going to report this one?
0.33.
Exactly. Remember this minus sign. Okay?
Okay.
Are we good?
Yes.
Do we have units for that?
No.
No, because the log, it is the same unit as the y-axis, and we don't have units on this. Okay. Now we go further. Using your answers to A, C3, C4 determines the value of N and C. Include absolute uncertainties in your values. You need to you need not be concerned with units. So we are just going to calculate N and C, and we don't have to care for the unit. Okay? Now, how is N and C related to anything? Let us go back to this equation. Can you remember what is the gradient?
1.99.
No. Here. How N is related to anything? N, gradient is N. Intercept is log 2 over C, right?
Yes.
Okay, we got it from the first part. So we say here N is equal gradient. C is, intercept. Is log C over 2, right? Or 2 over C. Okay?
Okay.
So we know the gradient. So the gradient is 0.99 plus or minus 0.04, right?
Yes.
Okay, so we directly write. We don't have any further calculation with this one. Sorry. Okay for you now?
Yeah. Okay.
Okay. What about the intercept? So we have this function. Do you remember how if I say it is A is equal log X, can we get X?
Yes. I'll say A over log equal X.
No. X is equal 10 to the power A.
Okay.
Go and check what I have sent you recently.
Okay.
Okay? So from here, I can say 2 over C is equal 10 to the power intercept. Okay? Can I read this equation?
Okay.
What can I say about
What?
C over 2?
Um.
How should I go?
Mister, I didn't. Oh, I didn't get the question.
So I have 2 over C is equal 10 to the power intercept. So if I say C over 2, what is going to be?
Intercept the power of 10.
No. I'm going to go all the way as 2 over C is equal 10 to the power intercept. I'm going to put it all minus 1, right? So it is C over 2 is equal 10 to the power minus intercept.
Okay.
Then C is equal 2 times 10 to the power to the minus intercept. Do I know the intercept?
Yes. Yes. It is
Okay.
0.83.
So the intercept is going to be okay. Now, this is what we get. Okay? Remember, Dean, the intercept over here. Okay? We have this 10 to the power minus 5. We have this, what?
10 to the power minus 5.
10 to the power minus 5. Okay? Then actually what we see inside, that we have 10 to the power minus 5 over here. Okay? Are you following with me?
Yes.
Okay. Why did we get this 10 to the power minus 5?
This is already written.
It is already there, right?
Yes.
It is already here. It is already here. Okay. So let us substitute. C is equal to times 10 to the power minus, and here it is minus 0.33. So minus and minus.
Plus.
Okay. We do that on the calculator. Sorry, this is plus, this is minus 5. Sorry, the 10 to the power minus 5 is over here. This we get plus 5 because it is 10 to the power minus 5 over here. Okay? So this is what we get. 2 times 10 to the 5 plus 0.33. So we do this calculation.
It is 4.3 times 10 to the power 5.
Yes, exactly. Okay. Now we need to calculate the absolute uncertainty. How do you think we should proceed?
Maximum minus the average.
But how we can, this is the, how we calculate the average. This is one, the average, right? Is one the average, right?
Yes.
So we calculate another one using the line of worst fit. Right? We are going to calculate another one with worst fit. So C is equal to times 10 minus the line of worst fit did have a gradient of what? 0.4057, right?
Yes.
And we do the calculation. Can you get the value?
So, Mister, I will subtract 0.4057 from what?
No, it is minus minus, as you did before here. It is going to be 2 times 10 to the 5 plus 0.4057, right? Can you do the math?
0 point what?
This one. 0.4057.
Okay, it is 6.9 times 10 to the power
5,
the power
right?
5.
Okay.
Yes.
6.9 times 10 to the power 5. And this is for the worst fit. So what is delta C? Can you guess?
What did you say?
What is delta C? The uncertainty in the intercept.
Subtract 6.9 from 4.3.
Yes. It is going to be 1.6, right? Right?
2.6.
Why 2.6? Yes, 2.6. So we get something like 3, right? To one significant figure.
Yes.
Are we sure we're getting this? Let me check it with my calculator. This might be a little bit off. Can you check your calculation again, Dean?
From which one?
For this one?
You mean 6.9 minus 4.3?
No, this one, 6.9. This 6.9.
Okay, I will.
Can you see it here? It is shift 2 times shift 10, and we have 5.4057. Right? Right, Dean?
Yes, okay. It came 5.1 times 10 to the power.
5.09. 5.09,
Yes.
right?
Yes.
5.09 times 10 to the 5. So it is 5.01. 5.09 minus 4.3.
Okay.
It is 0.79, right?
Yes.
And we keep it to one significant figure,
0.8.
0.8. So we say it is 0.8, and we keep here to how many decimal places?
1.
1. So we are done with this part. We have to make a bracket so to make sure that 10 to the 5 multiplies everything inside. And we don't have to care for the units. Are we okay?
Yes.
Okay. Now he is telling us, this is the final. The experiment is repeated. Determine the length L of the rod that gives a value of T of 0.1 millisecond. The experiment is repeated. Determine the length L of the rod that gives a value of T of 0.1 millisecond. So let us see the equation that we use. We are given this equation, right? Is it right?
Yes.
Okay. Do we know L? He's asking for L.
No.
Sorry. He's asking for L. We are given T and we are asking for L. So let us rewrite this equation.
TC over 2.
Are we okay?
Then L equal, we open a square root. Outside the square root, we write n.
Yes, it is 1 over n, right? Oh, the
Yes.
nth root, right? You were saying it is going to be like this, right? Is this what you mean?
Yes, yes,
Okay, so this is
yes.
actually can be written as Tc over 2, 1 over n. Okay? This is the nth root. Good. So we just substitute. So we know t is 0.1 times 10 to the power what?
-3.
-3. Do we know c?
Yes.
How much?
It is 4.3.
Times 10 to the 5. Right?
Yes.
Okay, 4.3 times 10 to the 5. Don't miss those things. Don't lose
Okay.
marks for nothing, okay? Divide by what?
Okay.
Sorry?
2.
2. And we
2.
get the nth root. 1 over n. What is n?
0.99.
0.99. It is almost 1, right?
Yes.
Okay, so can we do the calculation?
Yes, the answer is 2.2. To how many significant figure?
Just give me the result first, then we can check the significant figures.
22.1767
22,
2618.
22.17, right? Is that right?
Yes.
Or I'm missing something?
It is 22.17672
Okay, this is enough. 22.176 is enough. Now we need to check how many significant figures we should use, right? Is that right?
Yes.
How many significant should we use?
2.
2. Why?
Because of the 4.3.
It is 4.3. It is 0.99, also 2 significant figure. The 10 millisecond is also 2 significant. So it is good choice to go for 2 significant figure. But we are also, as remember, we are also good if we use one more significant figure, right?
Yes.
Okay, so we can, if it will be fine if you say it is 22, and it is also going to be okay if you say it is 21. Okay?
22.2.
Sorry? Okay, 0.2. So does it things look fine for you?